your seminar.
Okay, thank you very much, Professor Verma and Jantan, for organizing this and giving me an opportunity to talk about this one. As I'll try to, since I cannot see the faces, I'll try to go at the speed I'll try to adjust my speed, but please stop me or tell me if I'm going too slow, and I'll adjust accordingly. So I'm going to talk about Lyubeznik numbers, and these Lyubeznik numbers are basically certain bus numbers of local cohomology modules, which has some very nice properties, which has been studied, let's say, which was introduced by Lyubeznik in early 90s, and then afterwards it has been studied quite a fair amount, and especially there has been some generalizations of these Lyubeznik numbers in last 7, 8, 10 years. So it has been a fairly active area of research. I'll try to give some glimpse of this area. I don't claim to sort of cover every aspect of it, but I'll sort of try to address some portion of it, and I'll be fairly happy to continue the discussion afterwards also. So let me just start with some basics. So let me define what's a local cohomology first. So let S be a Noetherian local ring, and suppose F1, F2, Fl be a bunch of elements in S, and I'll define a complex, sort of a check complex basically. This is the following. I mean, you start with 0 and you take the ring S, and you localize S at these elements Fi, and you take their direct sum. Afterwards you localize twice. You basically take the products of two different elements and localize them, and so on. You go accordingly until you basically localize all of them simultaneously. This will be a complex if you define the maps, the differential maps, via localization with appropriate sign combination. Then this will be a complex. By that I mean the composition of two successive maps will be 0. For example, if L is 2, this is, first of all, this is going to be your complex, and the first map will just be an element going to small s going to S over 1, comma S over 1 in both those will be the components. And the last map will be, if you have taken element S over F1 power A and S prime over F2 power B, it's just going to be S over F1 power A minus S prime over F2 power B. And the other, if you take L greater than 2, accordingly there will be signed combination, and one can fairly, in a fairly easy fashion, check that these composition of two successive map will be 0. And that's why basically you take these signed combinations. You want them to be 0. So this is what is called a check complex in this context, at least. The ith cohomology module of an S module M supported at this ideal generated by those elements F1, F2, Fl is going to be basically, so this is we started with a complex. So if you tensor with M, of course it remains a complex. I mean, composition when you tensor with an M, tensor a complex with, basically you get a new complex where the modules are basically M tensor the modules of the previous complex, and the differential maps are just tensor between the previous differential maps and identity map of M. And of course, by functoriality, since the previous one was a complex, this one will also be a complex. The ith cohomology module of this complex will be called the local cohomology of M supported at ith local cohomology of M supported at capital I. So this is how it is defined. These local cohomology modules have some really nice properties, but we'll discuss a few. But first, let me mention perhaps the most important property, that this local cohomology module is unique up to radical of the support. That is, if you take two different ideals with same radical, then local cohomology module supported at them will be same. So just to give you one example, if you take R to be a polynomial ring in one variable where over a field, and you just take I to be the maximal ideal generated by that variable, the indeterminate. It's not too hard. It's not trivial, but it's not too hard to check that ith the local cohomology module is 0 if I is 0 or I greater than 1, and first local cohomology module is isomorphic to R adjoint X inverse. So you basically take Kx comma X inverse and co-mod this module inside that, this Kx. This is going to be your local cohomology module. Local cohomology modules of this particular ring with that ideal as support. So there are some really nice properties of local cohomology module, but there are a couple of long exact sequences associated to these local cohomology modules that I'm going to use today at some point or other. So let me just first mention them. So first is the Meyer-Vietaris property, that I and J be two ideals in a Noetherian ring S and M is an S module. Then there exists a long exact sequence starting from 0, goes to first 0th local cohomology module of M supported at I plus J. Then it goes to direct sum of 0th local cohomology modules of M supported at I and 0th local cohomology module of M supported at J. Then it goes to 0th local cohomology module of M supported at I intersection J. Then you kind of have this connecting homomorphism, which essentially, we all have seen this in context of snake lemma and many other cases where you get this long exact sequence. So this connecting map takes you to first local cohomology module supported of M supported at I plus J, then again direct sum of the first local cohomology modules, then again first local cohomology module of M supported at I intersection J, then again the connecting map going to the second local cohomology modules. So this is a long exact sequence you get for two ideals in S. There is also another long exact sequence related to localization, which is used repeatedly. Again, Noetherian ring, finitely generated module, and I is an ideal. Suppose you take also an element X, suppose J equal to I comma X, then there exists a long exact sequence. So the first one is 0 local cohomology module supported at J, which is I comma X, then 0th local cohomology module of I, then 0th local cohomology module of supported at I of M localized at X. That is, you invert the element X, that is, take the 1 over X power M's and so on, and then connecting again takes to the first local cohomology module of M supported at J and so on. So these two long exact sequences, Meyer-Vietaris long exact sequence and this localization long exact sequence, they are really important and they are used repeatedly. By the way, I'm not trying to give any overview of properties of local cohomology by any means, and you can see any standard text. And there are many other properties, like, for example, they are non-vanishing only between depth and dimension and so on. There is also local duality, which is fairly important. Those things are used, but I'm just giving you the basic glimpse. But one really important thing for local cohomology is that they're not usually finitely generated. They are in most of the cases, they are infinitely generated module. However, they share many interesting properties of finitely generated modules. That makes them, amongst many other things, that makes them so of much interest. So one example is that, for example, if you take n-dimensional regular local ring, SMK, one has the nth, the highest local cohomology module of S supported at M, the maximal ideal, is the injective hull of K, the field, over S. It's known, so the injective hull is basically the minimum indecomposable injective module, minimum injective module containing K, or I mean, it's true for any module over, basically any module over ring. Their existence depends on Zorn's lemma, and these are indecomposable injective modules, basically, so you cannot write them as direct sum of smaller injective modules. And these are known to be infinitely generated. So next we introduce this notion of Bass numbers. As I said, there's Lyubeznik numbers are basically Bass numbers associated to local cohomology modules. Given any module M over S, take a minimal injective resolution of M. Basically, minimal injective resolution is what you do is you start with M and take the injective hull and keep moving basically. So each component of that injective resolution will be isomorphic to a direct sum of indecomposable injective modules ES S mod P, where P is a prime ideal. That is injective hulls of S over P over S, this ring S. The number of copies of ES bracket S over P in ith position is called the ith Bass number of M with respect to the prime P. They are denoted by mu I P comma M, and they are equal to the dimension of this X module. Now observe that MP is a local ring over, sorry, MP is a module over local ring SP, and PSP is the unique maximal ideal of this local ring SP. So when you take SP mod PSP, you basically get a field. So this notion is of dimension of this module is essentially a notion of vector space dimension. Of course, a priori these dimensions can be infinite, but nevertheless, it makes sense to talk about dimension as in vector space dimension. So these dimensions are called ith Bass numbers of these modules. And observe that when I started, this module M is not assumed to be finitely generated or anything. And also one thing I should mention, that this construction of injective resolution, like by successively taking injective hull, this is free of a set of generator of M. So it's kind of natural in sort of category theoretic sense. So these Bass numbers, we will study a special case of these Bass numbers, namely Lyubeznik numbers. Bass numbers of local cohomology modules of the form Hj supported at I, S, are finite when S is assumed to be regular ring. This was proved in characteristic P by Huneke and Sharp in 1993, and also in case of characteristic 0, the same result was proved by Lyubeznik. Using this finiteness condition, Lyubeznik introduced a set of integer valued invariants of rings containing a field, which are now called Lyubeznik numbers. So suppose you have a local ring field, which is a surjection, which has a surjection from a regular local ring containing a field. Suppose there is a surjection from S to R, where S is regular local ring, and we don't assume much on R except it's just a local ring. And suppose I denote the kernel of this surjection. Now take this corresponding Bass number. I mean, first of all, we assumed that Bass numbers of S, they are finite. I mean, we didn't assume. I mean, it has been proved by Huneke, Sharp, and Lyubeznik for all the characteristics. So you define this Bass number, namely this dimension of over K, X, I, S, K, comma, Hn minus J, S, and these are called the ijth Lyubeznik numbers of this ring R. Now, the immediate question, of course, is that why they are well defined. I mean, they are finite, of course, this has been proved, but we only started with a surjection. This can be any arbitrary surjection. Why they have to be finite? It turns out that they are finite. Lyubeznik proved that, and that's why they are well defined. And I'll come to that in a moment. But let's first discuss a little bit about these numbers. By the way, is the definition clear to everyone? Okay.
I have one question. In that expression of dimension K, X, S, where is R? Like how it's related to?
Well, so that's what I'm saying. See, that's the well-definedness. So let's go back to this. So basically, there is a surjection from S to R where I is the kernel. So basically S mod I is R. So R comes in that way. And of course, there can be another surjection from another regular local ring onto R where it will have another kernel. So there is a question of well-definedness, which I'm saying that I'll discuss that. And I'm telling you that it is of course well-defined. Otherwise, I mean, those numbers will not be defined. But
No, my question is why we are calling it Lyubeznik number of R then? Like we can just
because because if you change S and I in a sense that suppose you change it to S prime and I prime such that S prime mod I prime is also R, then it remains same.
okay, this presentation doesn't depend on the presentation of R. That's what.
It only depends on S mod I. That's it. Yeah.
Okay. Okay.
So invariant depends only on R, I, and J. In particular, it is independent of the choice of S and that of surjection. That's of course a crucial property one needs to discuss. But further, if R is any local ring containing a field, it's also invariant under taking completion of R at maximal ideal. So in that sense, you can extend the definition. Before I prove that, or let's okay, I don't think I'll be able to prove it rigorously, but I'll sketch the lines of the sketch the main points of the proof of this well-definedness. But before that, let me give you some basic properties of these numbers, which were proved by Lyubeznik in the same paper. So lambda ij is 0 if either j greater than d, the dimension of R, and I greater if j greater than d, dimension of R, and I greater than j. Lambda dd is not 0. The highest Lyubeznik number is non-zero, the highest possible Lyubeznik number. I mean, this first equation already shows that it cannot be non-zero beyond ddth position. Its ddth position is non-zero, and it's equal to 1 if R is analytically normal. This is something I'm not defining because I'll not discuss this last term. I'm not defining, and I'm not going to discuss this for this talk. I'll just skip this angle. So look, because of this vanishing and non-vanishing, Lyubeznik numbers can be presented as this matrix form, which is called it's basically a d+1 cross d+1 matrix, which is called Lyubeznik table. And because of this first property, it is upper triangular. That's how Lyubeznik numbers are presented. One quick example of Lyubeznik numbers comes in the following form. Suppose R be a d-dimensional complete local ring containing a field. Suppose that R can be written as S mod I, where Sm is a regular local ring which contains a field, and I is an ideal such that HJIS is non-zero if and only if J is height I. I mean, this happens to in the trivial cases also. Then only non-vanishing Lyubeznik number is the top Lyubeznik number, namely lambda dd, and that's also 1. Zero otherwise. So study of this Lyubeznik table and how for various cases these Lyubeznik tables look like, where does these zeros appear, and so on. There has been a considerable amounts of research in last 20-25 years. But let me first mention one rather intriguing property, given that this is a characteristic P seminar mostly, that these numbers are actually characteristic dependent. The following example by Alvarez, Montaner, and Vahidi, this comes from a somewhat combinatorial context. There exists a minimal triangulation of P2R, the projective space over reals, for which the ideal is the following: x1, x2, x3, x1, x2, x4, x1, x3, x5, x1, x4, x6, x1, x5, x6, x2, x3, x6, x2, x4, x5, x2, x5, x6, x3, x4, x5, and x3, x4, x5. For this, if you take the field of characteristic 2, like just z mod 2z, let's say, then the Lyubeznik table actually has three ones and rest are 0. And if you take k equal to q, the only non-zero term is of the 3/3th term, lambda 3/3. Remember the second property I mentioned here tells you that the top Lyubeznik number must be 0. Here, for this example, top Lyubeznik numbers are same in both cases. However, there are other Lyubeznik numbers which are non-zero for characteristic 2, but all the Lyubeznik numbers are 0 for rationals. So this says that this is another sort of one possible direction is to explore what happens for the characteristic P and why it's how much it is dependent on the exact characteristic. But more importantly, as lambda dd is non-zero always, there is actually a very interesting characterization of lambda dd by Lyubeznik and Zhang, Wenliang Zhang, that if R is a local ring containing a field and D is the dimension, then the lambda dd is actually number of connected components of Hochster-Hunicki graph of the completion of the strict Henselization of R. I mean, you can basically assume it's power series, quotient of a power series. That's essentially it means. This completion of strict Henselization. But it's this Hochster-Hunicki graph is something I'll come. And so there is already a kind of a combinatorial aspect to it. In particular, of course, since number of connected component is non-zero, so this will be non-zero. Some other results to indicate what is sort of known, that for Cohen-Macaulay and in fact even S2, the highest Lyubeznik number is 1. Lyubeznik numbers of a complex projective scheme is dependent on the choice of projective embedding, where it is embedded. And this is extremely different from characteristic P. And this was proved by Luis Nunes, Betancourt, and Emily Witt, that for characteristic P, Lyubeznik numbers of projective schemes are independent of the embedding. So, by the way, any questions so far? Now I'll move to sketching the proof of this well-definedness. I mean, I just stopped. I just tried to give some known results and the definition first. Now I'll go to the well-definedness and further results. Any questions so far? Okay.
I have one question. Suppose ring is Gorenstein, is there something more about the lambda ij?
More than knowing lambda dd are equal to 1?
Yes.
Yeah, I actually don't know. Gorenstein is, of course, Cohen-Macaulay, so lambda ddr will be 1. Beyond that, I don't know.
Okay, thank you.
Anything else? Any other question or comment? I know Professor Tony Putenpurakal is there in the audience. Does he know something for Gorenstein? Anything more?
No.
Okay. So to prove this well-definedness, we'll use a key functor used by the way, I'm taking, so there is a very nice survey by Luis Nunes and Emily Witt, from which I took some of the basics, and some of the proofs I'm taking are broadly from that survey, and also, okay, I had to look into some papers also, but most of them were broadly from that survey. So they give a proof in that, which was slightly different from the original proof by Lyubeznik. But the main idea is there was a functor motivated by work of Kashiwara, which was used by Lyubeznik in that paper to prove it. So suppose K is a field and R is power series within n variable, and suppose S is just basically add one more variable and also take power series over that. Suppose G is the functor from the category of R modules to that of S module in the following way. Take an R module, tensor it over R by S localized at x n plus 1, and then go mod S. This module has some interesting properties that will be used there. So you apply this module to, first of all, this is not only applied to, of course, finitely generated modules, it's also applied to other modules. That's why you can apply to local cohomology modules also. So if you apply to the jth local cohomology module supported at I, what you get is M tensor that is same as if you take J plus 1th local cohomology module supported at I plus one extra element. And xi of mn and xi of mgn, they are same for all modules m and n. These two properties will be used to show the well-definedness. So finally, so for the well-definedness, so let's just recall the definition once more. R is a local ring which admits a surjection from regular local ring containing a field. Suppose I is the kernel, the Lyubeznik number of R with respect to ij is defined to be as dimension, vector space dimension over K of x small I A comma h n minus j supported at capital I of S, and it depends on only R, I, and J. That is number of independent of the choice of S and that of the surjection. So also, if it is any local ring containing a field, this is basically completion. It's invariant under the completion. The stage of the proof, we have this is finite due to Lyubeznik's work and Honecky-Sharp's work. So it remains to prove that this is well-defined. Take another surjection, and suppose I prime is the kernel of that surjection. Since Bass numbers are not affected by completion, we may assume R, S, and S prime to be complete, and take S to be this complete in this power series ring in n variable, and S prime to be power series ring in n prime many variable. Now take this extended power series ring where you basically take n plus n prime many variable, and take the surjection which takes first n many variables to the images of pi, which was the first surjection, and the next n prime many variable to basically the images of the this should be pi prime, by the way. This pi double prime j zj equal to pi prime yj minus n. Pi of yj minus n doesn't make sense because pi is not a map from S prime. Sorry for that typo. So let I be the preimage of I, or rather preimage of 0 under pi prime, let's say. Then, I mean, it's almost automatically follows from these two results that you basically step by step extend, take one element at a time, and because of this equality and this equality, basically you can show that both of these numbers, both of these x are same as this x. Hence, these two will be same. So that's roughly how the proof goes. I mean, I know I left many details, but that's roughly how it works. Okay, so next I'm going to talk a little bit of behavior under localization. So here I worked on a project with Luis Nunes and Koji Yanagawa, where we studied the behavior of Lyubeznik number under localization. So suppose again R be a ring which is a quotient of regular local ring of finite dimension, and suppose you're working on positive characteristic, then there exists global bound for Lyubeznik numbers of all localizations. So you take any Lyubeznik number of R localized at any prime, there exists a global bound. There is a positive integer which bounds all of them. And the proof of this result actually use the notion of F finiteness and F modules. So F modules are essentially modules which are isomorphic to so a module M is F module over R if it is isomorphic to itself under Frobenius action, and if further it is started, if we start with a finitely generated module, they are called F finite. The crucial thing is local cohomology modules and also repeated local cohomology modules are F finite and they're F modules. So many of the F module theory techniques. So F modules were introduced basically to generalize the D module theory, which was used by Lyubeznik to prove this, finiteness of Bass numbers in characteristic 0. So F modules basically generalize them in case of characteristic P. We use that and F finiteness to prove this result. But unfortunately, Lyubeznik numbers are not that well behaved under localization, because good result goes only that far, because we found an example which actually shows that the highest Lyubeznik number can both go up and down under localization. So if you take this ideal I, which is intersection of x, y, y, z, z, u, and uv, the highest Lyubeznik number for I is 1. One can check. If you take this ring p, x, y, uv, if you localize at that prime, Lyubeznik number is 2, so it falls, it goes down. However, if you localize at pxy, the Lyubeznik number is 1. So it can go up, it can go down, both. So in case of square-free monomial ideal, the theory is well understood using Stanley-Reasoner simplicial complex. And basically, one has very well developed theory, and which has lots of combinatorial interpretations. So people started studying Lyubeznik numbers for monomial ideals. And one standard way to study general monomial ideal is to polarize them to get square-free monomial ideal, called its polarization. Graded Betti numbers, like if you, instead of injective resolution, if you take a projective resolution of a monomial ideal and its polarization are same. So as far as the graded Betti number and theory of them are concerned, it's enough in a sense to study square-free monomial ideals. Because, well, so polarization is an operation such that if you take the polarization, basically going modulo or regular sequence, you get the original ideal back. So essentially the resolution remains intact. So you can go back and forth and the Betti numbers remain unchanged. Fortunately, same thing is also somewhat true for Lyubeznik numbers. They remain invariant under polarization of monomial ideals. So just to give you an example of what polarization is, suppose I is x1 square, x1, x2, and x2 cube. So what you do is you basically, wherever a square or higher power appears, you just add some free variables. So for example, the polarization of x1 square is x11, x12. So x1 appears, highest power of x1 in the generators is 2. So you basically, so you need 2 copies of x1. So you take x11, x12. So this thing becomes x11, x12. There is no there is no higher power. So it remains x11, x21. And there are 3 power, and it's cubed. So you take x21, x22, x23. So from this ideal, we denoted this. I know this is a bad notation, but I chose this for this talk, IE. Generally, it's used IPOL, but for some reason, I chose this, and then only later I realized that I have chosen a really bad notation. You get I back from the polarization by essentially going modulo the following elements. X12 minus, sorry, x12 minus x11, x22 minus x21, and x23 minus x21. So you essentially go on a regular sequence, you go on regular elements to get the original ideal back. So the resolution remains intact, hence the graded Betti numbers remains intact. And the similar thing in a sense is true also for Lyubeznik numbers. You take a polynomial ring and M is its standard maximal ideal, and suppose this is a monomial ideal and IE is the polarization, and suppose SE is the extended ring. Suppose N be the maximal homogeneous ideal of SE, and suppose H be the difference between the dimension of SE and dimension of S mod I, SE mod IE and dimension of S mod I. Then Lyubeznik number I minus H comma J minus H at Lyubeznik number of The smaller one is say, or the original one is same as the ijth Lyubeznik number of the higher. So that's sort of that's how that's what I mean, that in a sense it's preserved under polarization. And the proof uses the notion of radical functor and the notion of square free modules is thing. Any questions so far? Because I'll go to a different topic. Okay.
I have one question.
Yeah, sure. Hello.
So while defining this G of that local cohomology, you wrote that that's a local cohomology of with support I comma x. What is that x? That's x
Where is
n
it?
plus 1, or what is that x?
Oh, you mean this one? Oh, that should be n plus 1. I'm sorry. I'm sorry. That should be n plus 1. X n plus 1. Yeah.
Okay. And one more question, probably that's a silly question. Why are you considering R contains a field while defining Lyubeznik number uh, for any R with
You will
help of
see. I mean, it gives. So, I mean, of course, for well-definedness proof, these calculations will be. I mean, honestly not so sure whether one can define things this
Otherwise,
way.
it
And
will be DVR, right? Content if it's not filled, so it's regular mods are mine.
yeah, it will be a DVR. Yeah, in that case.
Then why field is required?
Well, if it is a DVR, for example, what will be the notion of dimension there, for example?
Notion of dimension means?
You know, Lyubeznik number is an integer valued object, right? I mean, so it's the dimension of xi. I mean, if you take DVR, it is xi, you know, xik. The module will be xik of the local cohomology module. But then will you
That's
take?
a regular ring, right? That's a regular
Yeah. No,
DVR.
you know, this is the. It is this thing, right? I mean, so in this case, for the dimension, this one will. I mean, you will have a DVR D there, right? What?
No, this K is the residue field, right?
Yeah. Okay.
So I'm saying that will be DVR at like some power series ring over DVR. So that will be regular local ring. So at least for definition, I can't see why you need containing a field.
Yeah, I don't know honestly. I mean, whether one can, whether everything goes through there or not.
Okay, maybe for some other calculation they need it probably.
Yeah, maybe. Whether the definition makes sense, yeah, I don't know. Yeah. Okay. So where are we? So now,
One more. In the definition itself, your local ring should contain a field.
yeah,
Or the presentation S mod I that S should contain a field is required. That was in the definition, or
no. So yeah,
okay.
I mean, so for example, in the definition of Lyubeznik number, so R is a regular local ring admitting a surjection from an n-dimensional regular local ring containing a field. Yeah.
Oh, okay, maybe that's why it is required that concern. Sorry. Okay.
Yeah. Okay.
There's a comment from Suresh. She says that the finiteness is known only when the ring contains a field.
Your voice is breaking. Can't hear it properly.
Sorry, I cannot hear anything. Voice is breaking.
Charge, they are known only when the ring contains a field.
Hello.
And Tarangam, I think your audio is switched on 2 devices. You may.
No, that's okay. I mean, I just
There
changed
was
it. Is it okay now?
No, not Arindam. Tarangama, I think.
Yeah.
I muted it.
Okay.
I'm sorry.
It's okay.
Jensen, was there one more question which I missed? Sorry,
No. I
No,
think
it's a comment. Sudeshna says that finiteness of Bass number is known only in characteristic P and characteristic 0, not in mixed characteristic.
yeah. Okay. Yeah. Okay.
Okay,
Yes,
I'm sorry. Actually, that was known in 1993. Perhaps that's why Lyubeznik defines that Lyubeznik number only for rings containing K. But later, I think for generalized Lyubeznik number, this DVR case also taken care of. I mean, this mixed character generalized Lyubeznik number is defined for mixed characteristic. Perhaps there these things will be taken care of. Whether it is containing field or not, that will not. I mean, get any issue in those definitions.
Okay.
Tony, you have some comments about the mixed characteristic case for Lyubeznik number.
See, the for mixed characteristic for unramified it is okay, but for ramified regular rings it is not okay. This is still unknown. Bass numbers or finite is still not known.
Okay, fine. Thank you. Yeah.
Okay. So this much is for this localization. So basically, the highest Lyubeznik number, it can go up and down. It can go down both for under localization. And but although if you localize at, so there is a global bound for all prime ideals, and it remains invariant under polarization. So that's kind of that is sort of the that's all at least we had in that paper. So I'll move on to a slightly different topic, namely now I'll discuss this result where I was discussing at the beginning, this result by Lyubeznik and Zhang, where it says the highest Lyubeznik number is equal to number of connected components of Hochster-Hunicke graph. So now I'll discuss that. So by the way, Hochster-Hunicke graph is something which keeps coming on various occasions, also in the combinatorial commutative algebra. It keeps coming. So suppose B is a local ring. The Hochster-Hunicke graph is the following. You take as its vertices the top dimensional minimal primes, or if it is unmixed, all the minimal primes, and two vertices are joined if by an edge if their sum of their height is 1. I mean, P and Q, both of them have height 0 because they're minimal primes. If their sum is 1, then they are joined by an edge. To give you an example, take this ideal. I mean, if some of you are familiar with notion of edge ideal, it is just a pentagon basically. You're taking x, y, y, z, zw, wt, and px. Here, the primary decomposition for that edge ideal is you just keep taking the vertices of pentagon and sort of vertices of its take a vertex and take its opposite edge, and take that vertex and the two vertices of the top opposite edge. Those prime ideals give you the minimal primes. So for Hochster-Hunicke graph, these will be its vertices, and keep taking some, and you will see that the only possible edges are P1, P3, P2, P5, P3, P5, P5, P2, P2, P4, and P1, P4, P1. So the Hochster-Hunicke graph will also be a pentagon. I think there is a typo. P2, P5. No typo. P2, P5. Sorry, I put it twice. So there are only 5 edges. P1, P2, P5 just appeared twice, but just ignore one of them. But more importantly, the Hochster-Hunicke graph of edge ideal of a pentagon is also a pentagon. Some more example. Take QXYZ, localize at XYZW, and take the ideal I, Z square minus 3x square, W square minus 3y square, ZW, 3xy, ZW minus 3yz. Note that if you take S mod I, it's a domain. A domain is, of course, has only one minimal prime, namely the zero ideal, so it has a single vertex. However, if you take the strict Henselization, it becomes this.
Arindam, I'm sorry.
Yeah.
Can you just go back to the previous slide?
Yes.
Out in the definition. So two distinct vertices P and Q are the primes, right? Minimal
Top
prime.
dimensional, top dimensional minimal.
Yeah. So, I mean, height of P plus Q is
Arindam,
1.
we are not able to listen to your voice.
Yeah. No, I think. Yeah. Can you hear me now?
Yes.
Okay.
Yeah.
No,
You
height
didn't
of
hear me
P
because I was
plus
not
Q is
speaking.
1.
Yeah.
Like in this case, if you take height of, height of P1 itself is
Okay. So P1 in B. I mean the image of. So P1 is an ideal in K is ZWT. It's image of P1. The ring is this. B mod this.
okay. I'm sorry. Yeah.
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 So here gamma R is single vertex. However, if you take the strict Henselization, gamma B has two vertices, of course, here. And if you take the sum of those two, that's actually 2. The heights of the sum will be 2. You will actually get X, Y, Z, W, all of them there. Sorry. So basically, gamma B, the highest Lyubeznik number is 2 there. So finally, I'll try to discuss a bit of this proof. This is basically highest dimensional Lyubeznik number is equal to the number of connected components of the strict Henselization. So the strict Henselization, again, I'm not getting it. You just can assume the ring is quotient of power series. That's why. This was done by Lyubeznik for characteristic P, and Zhang proved it, gave a characteristic free proof. There are several proofs that I'm kind of taking bits and pieces from many places. So I took some part from a personal communication between me and Luis Nunes Betancourt, some from his survey with Emily Witt, and also a paper by Walther. I'll just listed them at the end of this presentation. So lambda DD doesn't change under faithfully flat extension, so one can replace R with the strict Henselization, and assume R is a complete local ring which contains a separately closed coefficient field. Suppose gamma be its Hochster-Hunecke graph, and suppose gamma 1, gamma 2, gamma t be the connected components of the Hochster-Hunecke graph. So for dimension 1, note that Hochster-Hunecke graph is singleton, because either it is just a singleton vertex or all the connected components. For dimension 1, basically the Hochster-Hunecke graph becomes either a singleton or it becomes a complete graph. So it's either way, this is number of connected component is 1. Otherwise, suppose ij is the number of intersection of the minimal primes, then using Meyer-Vietaris, one gets this highest Lyubeznik number is of the highest Lyubeznik numbers of those intersection of minimal primes which belong to one same connected component. Hence, enough to show for equidimensional with connected Hochster-Hunecke graph. Now, so for d equal to 0, the Hochster-Hunecke graph is just a singleton vertex, 0 dimension. So the maximal ideal is the only vertex, so it's just a singleton. In this case, R is isomorphic to S mod I, and I is a maximal ideal, maximal ideal primary ideal. In this case, it's known that the 0th Lyubeznik number is dimension of the Sokol, which of the injective hull, which is known to be 1. For dimension 1 case, take R to be S mod I, where F comes from M minus I. We have a long exact sequence there. And from that, we get this short exact sequence. Long exact sequence of this, you remember we discussed this long exact sequence of localization. From that, we get this. So as radical of I comma F is maximal ideal, so the nth Lyubeznik number of nth local cohomology of I comma Fs is just the injective hull of K over S. If you take X to this, the second X basically is 0 because, this thing becomes, this is, F acts as a unit. So Sokol has to be 0. X0 is hom K of that. So which is hom K of something is the Sokol of that. And since this element F is a unit because it's a localization, so it's a module over the local module over the ring RF. So this element of M, this F acts as a unit, so that definitely cannot kill it. So Sokol by default has to be 0. So this second X is 0, and so the first X has to be 0. That's all right. So, but more importantly, the next map H becomes an isomorphism. Hence, the first Lyubeznik number is the following, which is basically dimension of K over K, which is 1. So these two settles D equal to 1 case and D equal to 0 case. The D equal to 2 case was done by Walther using Huneke-Lyubeznik vanishing theorem. In particular, he proved if I is intersection of primes where Pi is a prime of dimension 2, and if Vi minus M is connected, then lambda 2 to 0 and all other Lyubeznik numbers are 0. For D greater than equal to 3, one proceeds by induction, assuming the result holds for all dimension less than 3. As R is complete, one can write R equal to S mod I, where S is a complete n-dimensional regular local ring containing a separately closed field. Now, support of local cohomology module of S is supported on I has only finitely minimal prime elements. This was also proved by Lyubeznik. If associated prime of this module is not equal to M, then prime avoidance choose an element S which doesn't belong to either any minimal prime or anything in the support. If associated prime,
the previous slide, do you mean to say lambda 22 is not 0 and other Lyubeznik numbers are 0?
Yeah, sorry, that's what I mean. It's non-zero. Yeah, it's actually, yeah, that's what I mean. Yeah.
Okay.
So if it is equal to M, then take S in M, which does not belong to any minimal prime. Suppose S bar is the image of S in R. Since R by choice, R mod S bar R is an equidimensional, dimension D minus 1, and satisfies this property. And also Hoxton-Huneke graph of this is radical is connected. By induction, this finishes the proof. And so that's roughly the approach to prove this result. And I kind of rushed through this proof. So, okay, let me stop here.
Thank you, Arindam. We will take questions. People can unmute and ask their questions. Yeah, what is the interpretation for number of components of the Hoxton-Huneke graph?
What do you mean interpretation? Like,
I mean, here you are talking about it is connected. So if it is not connected.
So if it is not connected, then the Lyubeznik number is just basically, the number of connected components.
Okay.
Because of that identity at the beginning,
Okay.
Yeah, because of this thing. So you basically take all the intersection of the minimal primes in a connected component. From Meyer-Vieteri sequence, you will get this to be the sum.
Yeah. But the lower Lyubeznik numbers, do they have combinatorial interpretations?
They do. So in a recent paper by Louis, Emily, and Sandra Spidov, they also defined some sort of, certain generalizations of Hochster-Hunicke graph defined by higher connectivity. It's just sum of the height is 1, and they defined it for some to be higher thing. And some of the Lyubeznik numbers can be expressed in terms of those graphs. Yeah, there are some connections.
Oh. Okay.
I have one question, probably not related to this much. What is the motivation of defining this Hochster-Hunicke graph?
Well, so I think this was first defined by Hochster and Hunicke in this paper of this. Just one second. Yeah, it was defined by them in this paper, Indecomposable Canonical Ring, Indecomposable Canonical Module paper, and where they studied some. Yeah, I mean, it was basically defined for study of local cohomology and canonical modules in that paper.
Okay, and then why they are interested in completion of strict hensization of R?
So that you can basically use them as a quotient of power series ring. I mean, all
Okay.
this Sokol of K over this and that, all these things were heavily dependent on power series property.
Okay, thank you.
Yeah, so you basically, because it's a faithfully flat extension, you can pass through the completion and then sort of work there. So when you're working there, it works for a quotient of power series, basically.
Okay.
So what are the situations where we don't know how to calculate them?
Well, for monomial ideals, we know how to calculate because there is an algorithm by Alvarez, Montaner, and either just him or him and Vahidi to compute Lyubeznik numbers. I think for FPO rings also it can be computed. But I think that's it, I guess. I mean, like by computation, if you mean algorithmic computation, I think that's it. And the issue is to compute that you have to have some hold on local cohomology modules. So, so Stanley Reasoner and FPO, I think that's it. I don't know whether there is any other nice class where it can be. Whether even for I'm not sure.
Hypersurface or complete intersections.
Yeah, yeah. I mean, theoretically, yes, but so probably, yeah.
Okay. I don't see any other questions. So, Arindam, thank you very much for your very interesting talk. So next